Okay, so here's where we left off last time. We were talking about lines and planes and stuff. The next example. So suppose you are given a couple of planes, okay? And the question is to find the line, and specifically find a parameterization of the line that's parallel to both of those planes, right, and also passes through a given different point. So this is an example of one of these kinds of puzzles. You may recall I made a reference to this last time. There's lots of these kinds of questions where there's some givens, and then you want to find a related object. The givens tend to be algebraic. Right? So here's some algebra, a couple of planes, and the goal is to find some more algebra, namely a parameterization of the line. Right? So when you find yourself in this sort of situation, really the best broad stroke approach to the problem is first to realize, what does this mean you're given geometrically? What are the related geometric objects that you know? And what are the related geometric objects that you need? So let's talk about the planes, right? So we were given these equations right here, and that tells us certain things, but among others, it tells us that we know these normal vectors. Remember, you can read the normal vectors straight off of the coefficients in the equation, and it's a pretty neat trick, right? So geometrically speaking, then, I know these two normal vectors right here. Okay, now what do I want? I want a parameterization of our line, and if you want to parameterize your line, keep in mind you need two things. You need a point on the line. Hey, that's no problem. We already know the point on the line. That's just straight up given. Right? So I don't really need a point on the line anymore. I already have it. And then the other thing that I'm going to need to do a parameterization is I'm going to need a direction vector. So I'm going to need this vector here parallel to the line. So algebra aside, in some sense, the way to think about this question is I'm given these two vectors, normal vectors to the given planes, and I want to find this direction vector parallel to the desired line. And now we have a geometry problem. Now the next stage is going to be, and this is different for every question, but use the tools in your toolbox, play various games, solve various puzzles, and try to connect the dots and figure out how to take what you're given and produce what you need. So in this case, it's kind of a one-step process. I need a vector, let's see, parallel to the line. The line is parallel to this intersection. It's parallel to both of these planes, which means it's got to be perpendicular to these normal vectors. Let me say that again more succinctly. I'm looking for a vector perpendicular to two known given vectors. And we have a tool exactly for that purpose, and that's the cross product. Right, so I'm just going to cross product N1 and N2. Boom, I've got my direction vector, and bam, I've got my parameterization. Everybody see how that works? Everybody happy with this example? Right. Again, all these examples are different. So don't try to memorize your way through of how to, every single possible, version of, given a line and given a plane, find the line perpendicular to this and parallel to that, or, parallel to this and that passes through that, and there's too many different possible such cases. So try to reduce it to a geometry problem, and then just think creatively about how to sort of connect the dots. Okay. All right. So now next I want to give you a little bit of a warning. And the warning is about what I'm going to call transitivity arguments. I actually just did an example of a transitivity argument here. So specifically, I argued that because this vector is parallel to this plane, right, and the plane is perpendicular to the normal vector, it must follow that the vector must be perpendicular to that normal vector, right? So this is a transitivity in the sense that orange connects to blue, and then I should just be able to go straight from there to there, or something along those lines. We did a transitivity argument of sorts with the last example we did last time. And that was that, let's see, the plane was perpendicular to that normal vector, and that normal vector is perpendicular to the y-axis, and therefore we concluded that the plane has a geometric relationship with the y-axis. So again, a kind of a transitivity of sorts. So cool, it's fine if it works, but the sticky wicket is you should keep in mind that transitivity arguments don't all work, right? And I've seen it a million times on exams that students will make what symbolically, semantically feels like it ought to work, but geometrically it's just nonsense. Right? So here's a couple of examples of transitivity landmines, you might call them. Here I have a vector that's parallel to a plane, and then that same plane is parallel to another vector, and it's tempting, again, if you just look at the semantics of it all, or the notation of it all, you'd think that there should be some geometric relationship between V and W, but not even close. Right? There's just nothing. They're not parallel. They're not perpendicular. They could be. Maybe they are. Maybe they aren't. But the point is, what can we conclude? Nothing. Right? Is everybody on board with that? Okay. Likewise, with this example down here with planes, P and Q are perpendicular, and Q and R are perpendicular, but there is no particular relationship between P and R. And again, symbolically, you're tempted to say, I don't know, maybe two perpendiculars would feel like they would add up to a parallel or something, right? But it just doesn't. Okay. So heads up on that. Now, I want to tell you what the course policy is on using these kinds of transitivity arguments, and the course policy is go ahead. It's all good. Just make sure that it's true. Right? So if your argument relies on a transitivity, if that argument that you're making is valid, then it's allowed and all good, more power to you. And if it's not, then it's bad reasoning and you're going to lose points. Okay, is everybody happy? Is everybody on board? Okay. All righty. Okay, moving along. How do we parameterize a plane? This is a lot like parameterizing a line. The idea is if you have a given, let's see here, I got to choose my points carefully. If you have a given point, and if you want to find the plane that is parallel through that point and parallel to two given vectors, the big idea is you can start at your given point. You can move by arbitrary amounts in the direction of the v vector just by adding scalar multiples of v. You can move by arbitrary amounts in the w direction by adding scalar multiples of w. And therefore, by way of adding scalar multiples of v and adding scalar multiples of w, you can get from your starting point A to any point you want in the plane. Right? So that means that this is a parameterization. S and T can be any numbers, whatever. Right? Let S be any value you like, T be any value you like. This will produce a point in the plane, and furthermore, every point in the plane, I'm just going to make a geometric appeal here, every point in that plane can be reached by some appropriate choices of S and T. So this generates the entire plane. It's a lot like a parametric line, you'll notice. Just kind of two-dimensional, and therefore two direction vectors, and therefore two parameters, S and T. Everybody all right? Okay. So a quick example on that one. If you want to parameterize this plane, you may recognize this plane going through 3 given points. And we last time talked about how to find the equation of this plane through those points. Parameterizing is actually easier. As it turns out, we're going to rip off our first move from that previous example by subtracting 1 point from the other 2. Note that those are parallel to the plane. This is a total rip-off of what we did last time. To find the equation, I needed a normal vector, so I had to do like a cross product or something. But here, I don't. Here, I just need any point in the plane. Whoops. I have 3 of them. I'm going to pick A for no particular reason, other than that I like small numbers. Right? And now I've got these 2 direction vectors. And we'll use, again, S and T as my parameters, and done. Parameterization of that plane. Everybody good? All righty. Okay, so there's a large category of other kinds of problems involving lines and planes and points and equations and parameterizations and stuff like that. And that is distance problems. What's the distance from this to that? That kind of thing. So I'm just going to walk you through the broad strokes of the strategies. So again, please don't take this as a bunch of formulas to memorize. Right? Is not what this class is about, for one thing. But also, there's various different scenarios, and what if you're in 2 dimensions, and what if you're in 3 dimensions, etc. So the strategies is really what's going to pay off the most for you, is to understand how to what are the tips and tricks that will help you create such a formula rather than just memorize them pointlessly. Okay, so here we go. We'll start off with, if you have a point and you want to find the distance to a line like that, how do I find that distance? So first thing I have to point out is what do I mean by distance? And we know what we mean by distance from a point to a point, but a line is a bunch of points. Do I mean, when I say distance from a point to a line, do I mean that distance right there in green? Well, no, of course not. Right? In some sense, there's countless different distances that start at the point and end on the line. But when I say the distance, right, what I mean is the shortest possible distance, like that. And I hope that makes sense. As a for example, a plausibility appeal. If the line is the shoreline, right, and this is you out in the water, and the question comes up of how are you from the shore, right? This is obviously what we're talking about, right? I'm not interested in that distance there. If I'm going to swim back to shore, I'm going to swim the shortest possible distance. Okay. All right. So here's the idea. With your line, your given parameterized line, let's presume that it's parameterized, you have a point. That point you can subtract from the purple point, and you can get this. Let's see here. I'll use light blue. You get this difference vector there, which is not what I'm interested in. Right? This is some arbitrary displacement from an arbitrary point on the line to the given point. But notice I can talk about the projection. Right? This projection vector. And that initial blue vector minus my projection vector, that is kind of exactly what we're looking for. That's the vector D whose magnitude is the distance that we're interested in. So that's the big trick in this case. Given a point and a parametric line, pick any displacement vector, subtract the projection, you've got what you want. Everybody see the strategy there? Okay. All right, now here's another way. Different strategy. Same punchline. Pros and cons. You can. I've already forgotten what colors I used there. Let's see here. Yeah, blue and red. Okay, so we've previously set it up with that blue vector and this red vector, and a real clever little argument. I think this is nice. If I ask what this area is in yellow. Now, reasonable objection. Yeah, that wasn't the question. We were not asked to compute the area of that parallelogram, so why are we talking about it? Turns out there's a bunch of examples in math. We've actually kind of already seen one. I made a vague hand-wavy reference to it anyway. That if you find an unrelated object to what you're interested in, that you can connect, that you can compute in two different ways, at least one of which connects to what you're interested in, then you can actually end up inadvertently with an answer to a question. So I'm going to point out first that area is height times base. All right, old formula from high school geometry. I also know that area is the magnitude of the cross product. And not that I particularly care about area, but calculating area has pointed out to me that these two things are equal. And notice what I am interested in, that distance d, is involved in those two things that are equal to each other. And so just solve for d, boom, formula, and that works really nicely as well. Everybody good? Yeah.
Ideally, should both of the methods give you the same answer?
Oh, they 100% better give you the same answer. Yeah, and I'll say this, that any two valid calculations definitely will give you the same answer. And so if you do it two different ways and you get different answers, something's gone wrong with at least one of them. Absolutely, yeah.
I just want to make sure that I'm understanding the picture. Is D like the diagonal area?
It's the perpendicular distance. So given a line, there are a lot of different distances that you might call distances in some sense, but only one of them will be a distance that is the what you might call perpendicular distance, or this line segment is perpendicular to the line in question. Yeah, does that make sense? And so just now, geometric appeal, right? I'm not going to prove this. Not so hard to prove, but geometric appeal, the perpendicular distance is going to be the shortest. Yeah.
It was just hard to see from the photo if it was perpendicular like this way or perpendicular like that.
I gotcha. Yeah. Right. Okay. Cool. All right. Here's a nice one. How do you find the distance between two planes that are parallel to each other? And by the way, they better be parallel to each other. If they're not parallel to each other, they intersect. And if they intersect, then the distance would kind of have to be zero, because there are points that are in both, and it just doesn't make any sense. Okay, so parallel planes. Again, you can kind of naively say, okay, well, let's take a point in each plane and let's look at that displacement. That's a distance. How about that? Maybe we just call that the distance between the planes. But you can't, because that's not what distance means. Distance between two geometric objects means the shortest of all possible distances. Any point on the one, any point on the other. What is the shortest possible such distance? So if I just pick an arbitrary vector and look at that difference, that displacement, it's not going to be the shortest possible. The clever move is to realize that if you look at the part of that vector that's in the normal direction, right, that component is exactly what we're looking for. Well, almost exactly, but I mean, there it is, right? The whole point of a component is that it says how far is this vector in the direction of whatever the direction vector is, in this case, perpendicular, and so that will literally give us the perpendicular distance there. And the one little asterisk that I have to point out is don't forget to take the absolute value. The key point there being that components are not distances. Distances are intrinsically positive things. Components are coordinates, right? So they're scalars, but they're not necessarily positive scalars. So had this normal vector been pointing the other way, for example, the component would be negative. And all the negative means is that I arbitrarily picked the normal vector going the wrong way. The absolute value then would be what we would need. Everybody happy with that one? Okay. All righty. Moving along. This last one's really tricky. Suppose I have two skew lines. How do I find the distance between two skew lines? Keep in mind, skew means that they do not intersect and they are not parallel. Skew means the lines have nothing nice in common. They just no good news. They don't intersect. They don't point in the same direction. They're just kind of unrelated lines. How do we find that distance? This is a particularly scary-looking question because for any given point on the one, there's various possible distances, and I could talk about what the shortest of these various possible distances is, but how do I know for any such point that its shortest possible distance is the shortest of these possible distances? Right? So you got to consider all possible points on the one line and also all possible points on the other line. Right? So it's a hard question at a quick glance. Here's the thing that makes it straightforward. Beautiful observation. Whenever you have two skew lines, whenever you have two skew lines, you can always find a way to put those two skew lines in parallel planes. And it's actually not even that hard to do. Straightforward process. The big idea is that if you have these two skew lines given, we therefore can infer from the parameterizations these direction vectors. I can take those two direction vectors and cross them. Now I have a vector that's perpendicular to both of these direction vectors. And then any plane that I make that is perpendicular to that normal vector, well, again, transitivity, if the planes are perpendicular to the normal vector, and if the normal vector is perpendicular to these direction vectors, and again, you just got to think through the geometry and persuade yourself that this is a valid transitivity. These planes will all be parallel to these lines. And so then all you have to do is just kind of shift them as needed until they contain whichever line you're interested in. Right? So, said differently, pick a point on any one of the lines. That point, combined with your normal vector that you computed, will produce the appropriate plane. So, what have we accomplished here? I claim we're actually kind of done. The question was to find the distance between two skew lines. What I've done is I've effectively shown that the distance between these two skew lines is also the distance between two parallel planes, and we know how to do that. We know how to find the distance between two parallel planes. Previously discussed. Very clever move. Again, wish I'd thought of it. Everybody okay with this example? Yeah?
So the normal vector is not the distance.
The normal vector what?
Is not the distance.
Correct. The normal vector itself is not the distance. The distance is going to be a component in the direction of the normal vector. But you'd have to, pick one point in the one and another point in the other and look at that difference and then take the component of that difference. Yeah. Okay, so that finishes section 1.5, I guess that was, and we'll move along now to 1.7. Don't forget we already did 1.6 because I jump around a little bit out of order in chapter 1. So moving on to 1.7, different coordinate systems. Real quick, first I want to talk about the rectangular coordinate system. This is the one that you've known about since middle school, probably, right? The XY plane. And X coordinate, Y coordinate, all that business, right? And it's pretty straightforward. It's also got some really nice features to it. I'll point out, and this is not to be taken for granted, given a point, there's always exactly one X coordinate for that point. And there's also exactly one Y coordinate. So for every point, there is exactly one pair of coordinates and vice versa. So I like to say this as rectangular coordinates are unique. And it seems like a sort of a trivial observation to make. The reason that I like to point this out explicitly is sadly the new coordinate systems we're going to talk about, not unique. Right? Points are going to have multiple different, just different coordinates in, let's say, polar coordinates or spherical coordinates or whatever. All right. So another neat thing about rectangular coordinates is the rectangular coordinates themselves are the coefficients you would use in a linear combination of the standard basis vectors to produce that original point. So coordinates are coefficients in a linear combination. Nice. And by the way, just a quick callback to linear algebra class, and arguably in some sense this is the definition of what we mean by coordinates. Anyway, it's algebraically convenient. If you know the coordinates, then you know the corresponding coefficients. Arguably, depending on how you look at it, this is a special case of a more general fact that when you take a linear combination of vectors, you can take the corresponding linear combinations in the coordinates themselves. Very handy, very convenient for vector algebra computations and various kinds of arguments. Okay, so these as well will not hold in our new coordinate systems, right? So this, again, is sort of a peculiarity, a really nice peculiarity of the rectangular coordinate system, just like the uniqueness. So anyway, it's important to realize what you have to let go of when you create a new coordinate system. All right, so let's talk about polar coordinates. I suspect a lot of y'all have seen these before, but just in case, I'm going to describe them from the get-go here. Let's see here. So, so I like to think of polar coordinates as being a function. There is a function, and we'll write down the formula in just a moment, that tells me if you give me an r and a theta defined in a certain way, specifics coming momentarily, given an r and a theta, I can plug into a certain function and produce a point in the xy plane. Now, how am I going to use the r and the theta? The r and the theta work as follows. Theta, got my colors wrong. Sorry. Theta defines a direction. It does so by interpreting theta as the angle measured counterclockwise from the positive part of the x-axis to the direction that you want to go. And then r tells you how far to go in that direction. And now I appeal to your sense of geometry. If I start out thinking about just the zero direct, the positive part of the x-axis, straight to the right. If you tell me how far to rotate counterclockwise and then how far to go in that direction, you can get me anywhere in the plane that you want to get to. Everybody good with that? Okay. All right, now let me fix an asterisk here. You'll notice the quotes here on how far. How far implies a distance. Distances are unavoidably positive. In fact, R shouldn't be a distance. R is a coordinate. It should be allowed to be negative. Sometimes it needs to be negative. So we need to have a sense of what it means. What should it mean if R is negative? And it can't be a distance. Because, again, distances can't do that. So hopefully plausible is that if R is negative, then you just go backwards. Let's see here. I need a color. I guess I can use the dark green. If R is negative, you just go backwards instead of forwards. Does that make sense? Okay. All right. There's going to be a lot of situations, tragically, when I need to refer to something as it's going to be tempting to want to call it a distance, but it technically isn't. So I'll call it a distance, and then I'll come back and I'll clean up after the fact. Okay. Now, with that noted, I claim it's a pretty easy trig problem to look at this picture. Make a little right triangle. Notice that the x-coordinate is literally one of the sides of that triangle, and y'all remember high school trig and such, and therefore x is our cosine theta. I hope that's a easy little bit of trig for y'all. Again, this reminder, this course has not only a prerequisite, but a prerequisite trail. Right, so you have to make sure that you're proficient with all the stuff in the entire prerequisite trail. So linear algebra, sure, right, but also single variable calculus, but also trig, but also geometry, and also algebra, and et cetera, et cetera. So anyway, make sure you're good with your trig. Likewise, presumably clear the y-coordinate, of course. Again, one of the sides of the triangle, and so y is going to be r sine theta. All right. So a couple of things we have to deal with. They're not unique. Now, it's tempting to say that, okay, well, here's a point in the xy plane, and I can talk about the angle. Well, here's the angle, right? It's that angle right there, and there's some value of theta. I don't know. It looks like about pi over 3 or something. Pi over 3.5 maybe. So again, tempting to, at a glance, say that must be the theta that gets me to that point. And then if I go in that direction by a distance of, apparently 5, as I have this drawn, you would think, okay, well, then these must be the polar coordinates for that point. But here's the thing. Notice if you just add, I got to get better at, there we go. You just add 2 pi to the value of theta. In other words, if you just go around a whole nother turn, you're back to pointing the exact same direction again. So this value of theta, this greater value of theta, also gives you a set of polar coordinates that lands on the exact same point. So they're not unique. And by the way, you can add 2 pi anytime you want, right? As many integer copies of 2 pi, and it'll still just, every time you add a 2 pi, it just loops you around. How many times you go around doesn't change the fact that you're still pointing in exactly the same direction. Okay. All right, so there's infinitely many polar coordinates. Okay, it gets even worse. What if instead of 2 pi, what if you just add 1 pi? Notice that will take the direction you had been pointing, theta, and will then get you to, well, the exact wrong direction. And now, looking at this dark green direction here, right? Can I go in that dark green direction and get to this point? And, well, keep in mind, r does not have to be positive. So how far do I go in that direction? Just go minus in that direction, right? And that will again get you to that same point. So here is yet another set of polar coordinates that gets you to that same point. Okay, so in some sense there's two separate infinite collections of polar coordinates for any point in the xy plane. That's annoying. Okay. Here's another little annoyance. Now that we have two coordinate systems on the table, whenever we write down a set of coordinates, it is kind of unclear at this point which these are. Are these the x and y coordinates of some point, or are these the r and theta coordinates of some point? Which do I mean? And, well, it's tempting to look at the actual values, and you look at pi over 6 and think, you know what, pi over 6 looks like an angle. Well, okay, I mean, it kind of looks like an angle, but I'll have to recognize pi over 6 is a perfectly legitimate real number, and it could totally be a y-coordinate, right? So there's no way to know that this notation doesn't refer to the point with x equal 2 and y equals pi over 6. And there's also no way to know. Maybe it refers to the point with theta equal pi over 6 and r equals 2. I don't know. What's written down here just isn't clear. Right? So this is just a heads up. Notice how easy it is to clarify if you just write r comma theta equals 2 comma pi over 6. Now, it definitely is a reference to that, and it's definitely not a reference to that. So let's keep that in mind. Right? It's easy to do, easy to fix. Try not to be ambiguous in your work. And I guess I should point out, related to this, that I can only give on exams. I can only give you points for what I can confidently interpret from your work, right? And if what you've written is really, truly ambiguous, and I do not know what you meant by what you wrote down, I can't just assume the best, right? I have to grade based on what I can confidently interpret. So this is something to be careful about. Okay. All right. Let's see here. Moving along. Here's a surprisingly dangerous one. Some nice formulas. Again, you can look at the sort of the trig and the geometry of our little triangle that relates polar and rectangular coordinates. Easy to write down these little formulas from that triangle. A little bit of high school work. It's tempting to take it a step further and write down, I'm going to do this in red, and then I'm about to cross it out. So if you write this down, please do cross it out momentarily. Tempting to write r equals square root of x squared plus y squared, but you can't. Because this symbol here does not mean whichever square root happens to be convenient for my purposes, right? It's just not what that means. This symbol means something very precise. This symbol means the positive square root of whatever the number is under the radical. Right? So that symbol means positive. If this equation were valid, that would suggest that r would have to be positive. It does not. So this formula is wrong, right? You can't do that. Likewise, very tempting to sort of, if you will, solve for theta here and say theta equals, arctan of y over x. Again, not true. Arctan takes a very specific set of values, right? arctan can only be just, the negative pi over 2 to pi over 2, exclusive. So this would suggest that theta is likewise so constrained, which it is not. So again, this formula, not true. Everybody see the problem there? Okay. Now it's worse than this, I claim. Some students think, a lot of students think, that, okay, fine, but come on, surely I can use these red formulas up here, and that'll give me a set of polar coordinates for the given point, and then I can, I know how to add the 2 pi's with the minus sign, and you can just kind of manipulate. That doesn't work either. And here's the easy counterexample. Let's see here. Let's look at this point right here. -1 comma -1. There it is. Right? Now, you can easily confirm from the green formulas, you can confirm what r squared is, what tan theta is. Nothing to it. Right? And then if you were to trust these red formulas would seem to suggest that r and theta would have to be these values. Square root of 2 and pi over 4. Which would put you over here, which is the wrong point. So it's just wrong. And again, this isn't me just being uptight. This is me warning you about a landmine that I don't want you to step on and get a importantly wrong answer. Notice as well, this is not an obscure weirdo counterexample. Easy point, easy coordinates. Those formulas are just flat out wrong. So, heads up, please. Right? I think it's much better to abandon these formulas entirely and instead go with what I have in green, right? And then, sure, look at your possible values of r and look at your possible values of theta, and then think through the geometry, though, right? And thinking through the geometry should help you pick out what the correct values are, and let's go ahead and do that. Let's see here. So we have 2 possible values for r, right? And then we have what I'm going to loosely call 2 possible values for theta. Obviously, you can add any number of 2 pi's at any time, right? Totally. But these being roughly the 2 possible values, now you got to think through which is which. And again, the geometry will be your guide. So let's think in particular about pi over 4. Can I use pi over 4 as my direction? Can I let theta equal to pi over 4? And if so, what is the corresponding r? Well, plus or minus are my candidates. And I look at the picture. Geometry tells me where the point is that I'm interested in. Geometry tells me which direction I've chosen for my theta. And then the geometry that results tells me that I need to go negative in that direction to get to the point in question. So pi over 4 pairs with negative square root of 2. And then likewise, analogously, 5 pi over 4 pairs with positive square root of 2. Everybody happy? All right. Okie dokie. Okay, so a few examples. Oh, yeah, I'm sorry, go ahead.
I just had a quick question.
Yeah.
So putting negative root 2 pi over 4 would be right? Like we don't have to write the plus 2 pi in?
It depends on how the question's phrased. If the
Okay.
question says find all possible, then you got to put the plus 2 pi in. If it says find polar coordinates for this point, that didn't say find all of them. It just said find it. That phrasing would suggest any acceptable polar coordinates should be fine. Yeah.
Okay.
So it devils in the details. Yeah. Yep.
So would we be allowed to use a calculator, or would we be given like the different values of like theta, like tan theta?
So that's a great question. On exams, calculators are not allowed, and correspondingly, I would never give you something on an exam where a calculator would be necessary. right? So for whatever it's worth, I am going to assume that everybody is good with all of the standard angles, right? Any multiple of pi over 4, any multiple of pi over 6. You should know the trig of all of those. On the homework now, yeah, there's some weird angles that come up and some application type questions. On those, of course, there's nothing you can do. You have to use a calculator in those cases. But any time that you can do it without a calculator, you should do it without a calculator. That's right. Does that make sense? Yeah. All right. Okay. All right. Let's see here now. Let me look at the clock. Yeah. Okay. We're good. Okay. Yeah. Equations in polar coordinates. A couple of these are just kind of quickie little observations. Let's look at r equals 3. I think this is a pretty easy one, actually. This is straight up telling you distance from the origin is 3. Distance from the origin is constant. It's practically screaming, right, that we're talking about a circle. Right? Okay. But now let's suppose you hadn't noticed that. Slick move, if you want to turn the polar equation into a rectangular equation, in this case, the trick is to just square both sides of the equation. And having done that, notice that r squared shows up, and r squared is something that I have a pat, standard, easy peasy way to translate into rectangular coordinates. Right? And so my polar equation turns into a rectangular equation. And of course, you'll recognize that is the equation of a circle. So likewise for this one, different trick. Take tangent of both sides. Tan theta shows up. And again, this is one of our standard established formulas. Tan theta is y over x. And that converts me from polar to rectangular. Okay, so kind of a nice, easy one there. But sometimes you have to do a little bit more work. I'm going to come back to this example, the third example, momentarily, time permitting. This one's a little trickier. But again, I want to convert from polar to rectangular. It's just that this time it's a different trick. You see the r here, and it's very tempting to just square both sides. But the problem is if you get this desired r squared by squaring both sides, then the right side would turn into cosine squared, and I don't know what to do with that in rectangular coordinates. Right? So the slick move here, don't square both sides, just multiply both sides by r. Right? Multiplying both sides by r turns this into this, which is r squared, which I can convert to rectangular easily, and then r cosine, which I can convert to rectangular easily. That's how this one happens to work out. Right? They're all a little bit different. So, last thing I'll say on this example is I want to make sure everybody's good with the idea of completing the square. I know it's an old high school algebra thing that you may have thought was in your past, permanently in your past, but it's not. There's various little bits of algebra that don't necessarily come up very much in high school, but then, here and there really are super useful in various different contexts. So the law of cosines is another one of these. It's really handy. Not very often, but when it's handy, it's super handy. And likewise, completing the square. So you'll notice these terms turn into those terms. And if I just add a fourth on both sides of the equation, conveniently, I get a perfect square that allows me to rewrite the algebra into something recognizable. And this last line here, of course, you'll recognize is the equation of a circle. So it's a real slick move. How did I know that 1/4 was the correct number to add on both sides? That's the clever trick of completing the square. It's easily Googleable if you still have your old high school algebra books, which I bet you don't. But anyway, if you have a favorite reference, go ahead. Otherwise, Google it. But make sure that you're good with completing the square. It's a very useful technique. And it looks like we're out of time, so we will pick up here next time. And yeah, see you later. Have a good one. Oh, real quick.